All right. So sorry for the delay here. I lost one of my files I needed. Anyway, so just a bit of housekeeping. So on Wednesday, there's a spring break day. You all know that? Yeah. So there's no homework due on Wednesday. It's due on Friday instead. So if you look at Moodle, there's a turn-in link on Friday, but not for Wednesday. The other bit of housekeeping is that I don't want to waste a lot of time on this, but for the next 4 weeks, which is all we have left, Fridays will be Zoom days. So we'll be on Zoom instead of in the classroom. So apologies to Riley and Ben, and who've heard me say this already 3 times today, right, Ben? Anyway, but long story short, I have a new baby. My wife has taken her maternity leave, and now it's over. So we talked about this before the baby was born, that I would just take paternity leave when her leave was over. But in talking with my department chair and the administration here, I mean, of course, I have a legal right to do that, but it became clear that there was no good plan for dealing with my classes after I left. So I'm doing like a halfway thing. I'm still working full time, but on Fridays, I'll stay home with my kid. So on Fridays, you'll hear babies screaming in the background. My wife is gonna, or sorry, not my wife, my mom will be there to help with the baby. But the baby doesn't like my mom. The baby's a pandemic baby. She's not used to other people. So during class, that's all you're gonna hear is her screaming in the background. Although by next Friday, or by this Friday, maybe she'll like my mom by then. I don't know. We'll see. Anyway, so I'll send out an email about that just to remind you, but Fridays are Zoom only. Monday and Wednesday will be normal. So we'll see how that goes. See, because the baby will have to really like my mom by next Monday, I guess. So we'll see. Anyway, okay, so we're marching our way through chapter 9. We have one more section to do before we can do the ecological models, which are the culmination of chapter 9. So the thing about the ecological models that we'll get to, predator-prey and things like that, they're not linear. They're not linear systems, which is bad because all of chapter 7 and then all the stuff we did last time, you had to have a linear system. You all agree with that? So like, okay, well, if these models are nonlinear, then how are you going to use the linear things to study them? And this section answers that. This section shows how you can take the material we've been doing and apply it to nonlinear systems. And it's a really nice idea. It's a nice little callback to Calc 1. The idea is that even though a system might not be linear, it can be locally linear. This is an idea that should be intimately familiar to you from Calc 1, especially those of you who took Calc 1 from me. I bet you remember everything I said from Calc 1. Yeah. Is that right? Megan? Everything I said is in that mind, right? Because everything I said was so important and so well said. Now, as I have had to make more videos of myself over Zoom, I've become more and more aware of how non-compelling my voice is. Okay, so I already knew that before I made videos of myself, but I don't know. So I guess most of what I say, you hear from a boring voice that probably doesn't stick very well. But anyway, local linearity. Okay, so let me just unpack that phrase. Well, let me ask you, what does it mean for something to be locally linear? Say again, sorry. Let me apply that adjective to a noun, okay? What would it mean for a curve to be locally linear? Like say, here's a curve from Calc 1. Take the point off. Is this curve linear? I don't think so, right? Is it locally linear? And if so, what would that mean? Yeah, from 1 to 2, it looks like a line, right? Does everybody agree with that? Other places it's not, though. So are you saying it's sort of locally linear here, but not maybe right here? Yeah. Okay. This curve is actually locally linear everywhere. So what do I mean by locally linear? And again, this is something we talked about in Calc 1, but you probably haven't thought about it since then. To be locally linear means if I zoom in on you at a point, I see a line eventually. So right now, I don't have to zoom in on this part at all. I basically see a line. But what if you zoom in, say, right here, or whatever this point is? If you zoom in enough, that's not enough. Doesn't look like a line. That looks like a line. Still a little bowed, though, right? Am I sharing my screen? I'm not. I should. Anyway, let me zoom. Why would I now be muted? Did I hit mute? All right, well. So those of you on Zoom, I'm not sure what you heard and what you didn't hear. But anyway, I'm just making a Calc 1 point. You zoom in on a curve enough, you'll see a line. That's a familiar idea from Calc 1, right? Now, in particular, if you zoom in on a point enough, you'll see a line, but you actually know which line it is. Let me zoom out because I have a point preloaded here. See which point I cared about. This one. No, this one. Okay. So around this point, it doesn't look like a line, it's curved. If you zoom in enough on this point though right here, you'll see a line. Do you know which line it is? The tangent line. Huh? Calc 1, right? You guys remember tangent lines? I hope so. So here's the tangent line at that point, blue. So of course, globally, that black curve looks nothing like this blue curve, although I guess you can't tell it's blue on the screen. Those of you at Zoom finally have an advantage. You can see the blue. But now if I zoom in enough, but there's still a bit of a gap there, right? But if I keep zooming, now there's no difference between the tangent line and the curve itself. Okay, so anyway, that's the idea of local linearity. You zoom in on a point enough, you see a line. Which line? The tangent line. Now this is in contrast to other curves that are not locally linear. So let me zoom out again. Okay, so again, turn your Calc 1 brain back on. If I flash this up on the screen, and let me make the scale better. It's too zoomed out. That's even worse. What that negative space. Okay, this is an absolute value curve, right? What's bad about this in Calc 1? Yeah. Okay, at 0, there's a sharp point, and there is no tangent line, right? Y'all remember that? Sharpness is bad if you care about derivatives. So you can see that in terms of local linearity by if you zoom in enough. I'm going to zoom in. Do I see a line? I don't, right? But what if I zoom in more, right? So I'm only at negative 0.025. What if I do like 10 to the negative 100 or whatever I was doing before that scale? So I keep zooming in. Oh, it's the same picture. I still don't see a line. Zoom in. You see my point here, right? If there's sharpness or something, you're not locally linear. So to be locally linear, you have to have a tangent line. You guys believe me if I keep zooming in? See? It's like a fractal. You keep zooming in, you keep saying the same thing over and over again. My scale is really tiny now. It's still that sharp point. Okay, so anyway, that's Calc 1. That's the idea of local linearity. If you have a curve that's smooth, so a derivative exists everywhere, no matter where you zoom in, you're going to see a line. Now, of course, the line might be different, obviously, right? So sometimes you zoom in and get a line of slope 3, sometimes a line of slope 10, whatever. But that's the idea of local linearity. Zoom in and you see something linear. That same idea works here, actually. So these systems we've been dealing with, that we're going to deal with, in sections 9.4 and 9.5, while they're not linear, they are locally linear. So if you zoom in enough, you're going to see a linear system there. So it's a super nice idea. It's just that Calc 1 idea, but really beefed up now because it's happening in the phase plane and the x1, x2 plane, rather than, you know, y versus x or whatever from Calc 1. Okay, so let me just show you how that works with this example here. So here's a system. Now everything here is a function of time. It's just instead of using x1 and x2, I'm using x and y. Everybody okay with that? We're going to switch to ecological notation here at the end of chapter 9. So x prime of t is x of t times this thing. Y prime of t is y of t times this stuff. You see how this isn't linear? If you were to expand this out, you have like an x squared. That's not linear, right? X times y, that's not linear. So you can't write this as x equals like 2x plus 3y, y equals x minus y, whatever, right? That's a linear system. We can pull that matrix out. Everybody see that? This is fundamentally different now. If you hand this system to chapter 7 says, what do you want me to do with this? Everybody agree with that? Just outside of bounds, chapter 7. Okay. However, we can start thinking about it systematically by first thinking about equilibrium. So again, what's an equilibrium in this context? Something we defined last time. Yeah, as always, it's when the derivative is 0. You're looking for solutions whose derivative is 0. Okay, so to find equilibrium, we have to think about when x prime and y prime together are 0. And let's see what we get. So if you want to think about that, when x prime and y prime are both 0, what do? Hey, you set them equal to 0, and then what do? Yeah, you ask the computer to solve it for you. It's just an algebra problem. So having nonlinear things equal to 0 is a little more complicated than what you did in high school, but it's the same idea. You could still like isolate x and substitute if you wanted to 0 equals. So anyway, you just hand Wolfram this system like this. Make sure I type those correctly. And ask it to tell you what the solutions are of this. So again, all I've done is I've set the derivatives equal to 0 and asked Wolfram to analyze the consequences of that. Okay, so it shows me some stuff. But what I really need, where is all this? Okay. You scroll long enough, it tells you solutions, okay? So you handed it 2 equations with 2 unknowns, right? X and Y were both unknowns. So it's going to give you solution pairs. So when X is 0 and Y is 3/4, that's an equilibrium. When X is a half and Y is a half, that's an equilibrium. When X is 1 and Y is 0, that's an equilibrium. And finally, when Y is 0 and X is 0, that's an equilibrium. So this system has 4 equilibrium points, all of which Wolfram lists for you. So again, back on the handout, when it asks, anytime you want equilibrium, just like back in chapter 3 or chapter 2, whatever it was, equilibrium is always setting something equal to 0, which results in an algebra problem, which Wolfram will solve for you. Now, I want to process what that means in this particular context so we're all clear on what Wolfram is telling you. Okay, so here's my original system. Suppose x of t were 0. So over time, x is always 0. Suppose y of t were also always 0. Let's think about substituting those in. If x of t is 0, what's x prime? 0. Same thing for y prime, right? Okay, well, if x of t is 0, what happens to this step? 0, right? Because that x right there. And if y of t is 0, what happens to this? Also dies, right? So 0 equals 0 both times. So it checks out, you know? Let's take one of the non-zero ones. Let's think about this half-half, okay? If x of t is always a half and y of t is also always a half, they're constant solutions. Let's process that. Okay, so if x of t is always a half, what's x prime? 0. The derivatives are always 0, right? Because we're dealing with constants. Then I have a half here. Did I agree with that? X of t is a half. I have a half there and a half there because x and y are both half. So if you put a half there and a half there, what happens? 1 minus 1. So then you end up writing 0 equals 0. It checks out. Down here, what? I have minus a half, minus half of a half. Right? So I have 3/4 minus a half minus half of a half. What's that? 0, right? So when Wolfram gives you this data saying if you simultaneously plug in both x and y for each of those 4 pairs, you're going to get something that works out up here. You need everything dying to 0. Okay, so any questions or comments on this, what we did here, what Wolfram is telling you? So there's all sorts of X and Y pairs you can cook up that don't work, right? If you put X equals 1 there and Y equals 2 there, it doesn't work anymore, right? Wolfram is giving you the pairs that work. Okay, so now a bigger question for each of these 4 equilibria. If you were to look at the system itself, how is it behaving around those equilibria? So let me bring up the system. So I've, whoop, no, okay. So in red, can you guys see the colors all right? Probably not. So up there, there's an equilibrium. That's X equals 0, Y equals 3/4. Are you okay with that? This is in the YX plane. So T, again, T is suppressed. This right here is 50/50. This right here is 1, 0, X equals 1, Y equals 0, and there's 0, 0. Everybody okay with that? Okay, so let's pick an equilibrium and sort of think about how things are behaving there. Here's an equilibrium here, 50/50. I'm gonna go to that equilibrium and kind of zoom in on it, sort of see what's happening around it. Okay, this is what's happening around 50/50. Does this picture look familiar to you or not? Have you seen something that looks like this? Yeah, right. The attractor line thingy, he says, right? You guys recognize that? And that's right. Now your book will call this a node, right? But that's what it's saying. So this is a stable node right here, where the attractor line is the dominant eigenvector. Okay, but we saw this in the previous section, a picture just like this. Everybody okay with this? Stable node, and it came from a linear system, right? So if I zoom out here, this overall picture, right, if you let your eyes scan across the whole thing, we saw nothing that looked like that on Friday. You guys agree with that? However, if you pick an equilibrium and zoom in on it, like I just did, we saw a picture that looks like that. And in particular, so take a, here, maybe I'll try to do it side by side. Take a mental picture here of this. Okay. Look at these two things side by side. This picture here comes from this linear system. Let me write it out. So the picture on the left is this linear system. Old x prime equals -0.5, -0.5, -0.25, -0.5. That's what's in the blue picture there. Everybody okay with that? So, what is the punchline of all this? The punchline is this thing that's over on the right. Again, just to make the point, if I zoom out and I say, hey, look at this picture. Does this look like something from section 9.1? Does this look like a linear system? The answer is no. We saw no picture that looks like this. But if you zoom in enough around a given point, like this one, suddenly, oops, my scale's a little off here. Oh, maybe zoomed in too much, I don't know. Oops. Somehow I butchered the scale here, so it's killing my point. Why is it? Oh, sometimes this app decides to put things horizontally for some reason. All right, well, I'm going to quit messing with it, I guess. Anyway, we all remember what this thing used to look like when I zoomed in, right? It looked just like that. So you zoom in enough, you see a picture that comes from a linear system. Just like in Calc 1, if you take your curvy thing and zoom in enough, you see a line. That's what's happening here. It's a super nice idea. Now this link, by the way, I put it on Moodle. This is better than Desmos because you can control, I found this over the weekend, you can control the axes. So you can go from like -3 to 3 on the vertical or -3 to 3 on the horizontal, whatever. So if you want to use this one instead of the Desmos one, you can. This one here, by the way, it's very obnoxious though. Whenever you multiply things, you have to be explicit about multiplication. Okay, so you can't write -0.5x. If you do that, it's like, what are you talking about? Okay, and it should know exactly what we're talking about, right? -0.5x, we all know that means -0.5 times x, but this calculator doesn't know that. So I still haven't found a great calculator, but anyway. So if you want to use this instead of Desmos, you can. Again, it's nice because it lets you control the viewing window, and Desmos doesn't. Okay, now all that to say, for any of these red circles here, if you zoom in on them enough, you're going to see something like what we saw in section 9.1. Okay, so before I give you the sort of the theorem here that lets you determine what system matches that, are there any questions about the point I'm trying to make here? Around equilibria, you'll see a linear system. And the question is, which linear system? Any questions on that? Okay, so to describe, like, how did I know? How did I know if I zoomed on this red point here, I would get this particular linear system here? How did I know that? The answer is there's a theorem that tells you. Just like, again, with the curve from Calc 1, if I pick a point and say, well, what is the line that I would see if I zoomed in? There's a theorem that tells you, right? It's just the tangent line, and you can get that from a derivative. So we're going to do something similar here. So to do that, I need this notion of a Jacobian. Okay, so suppose you have a system, x prime equals x and y stuff, y prime equals x and y stuff. So f and g are just shorthand for this x and y stuff over here. So capital F is shorthand for the x prime equals stuff, and then capital G is shorthand for the y prime equals stuff. So in this case, in this example here, this is F right here, capital F. And this is G for this particular example. Everybody okay with that? Okay, the Jacobian of that system is a matrix defined like this. So we haven't used this language since section 2.6, so it's been a while. But this is the x partial derivative of f. This is the y partial derivative of f. X partial derivative of g, and then y partial derivative of g. So we're going to write these out in a second, but is this okay, that idea of a partial derivative from like 3 months ago? Most of you have had Calc 3, right? But those of you who haven't, do you remember that? If not, we'll review it here in a second. But all that to say, if you take partial derivatives and then you have a point that you care about, like say half-half, or say 1-0, whatever, you can then plug that point in and get a matrix just full of numbers instead of a matrix full of functions. So the Jacobian at a point is just plug in the point you care about and see what numbers you get. Okay, so given the example we just have, let's find the Jacobian and then zoom in on the point half-half. Okay, so let's see if I can move my computer without muting myself. Can I do that? Let's see. That was pretty good, right? Still not muted, okay. You know, even like a year later, it's still hard to keep all this stuff straight. When you're old, right? Not for you people. You people are young, right? Your minds are fresh. Y'all agree with that? Old people like me, it's hard to deal with Zoom all the time, things like that. And actually, if you don't mind me digressing a little bit, again, sorry for people like Ben who hear me say the same thing over and over. I have very limited material, right? But I remember one time when I first bought it, you guys know an iPod Nano. Remember those things? Little tiny things, right? So when I first bought one of those, it was like right before Thanksgiving. Then I went to my grandparents' house for Thanksgiving. And I remember getting it out and like explaining to my grandmother what this thing was, you know? And at first, her face was kind of curious, but then it just sort of like, what's the word, devolved or something, right? Into like confusion and horror, you know? Like her face was like, wow, the world is changing in scary ways. I don't understand what's happening anymore, you know? Like that happens to old people a lot, right? That's what my face looked like when people explained to me what Zoom was a year ago, right? At first I was like, oh, that sounds great. And people keep explaining, I'm thinking, my face, I could see it on the Zoom meetings, melting, right? And to an old person look of horror as the world changes around them and leaves them behind. Anyway, so I think I made it over here without muting. I guess that's my only point. Okay, so let's find the Jacobian of this system. So if you want to find the Jacobian, by the way, the easiest way to take partial derivatives is to expand everything out. So I'm going to write that x prime is x minus x squared minus xy like that. And then y prime equals 0.75y minus y squared minus 0.5xy. So now I have to build a 2 by 2 matrix consisting of partial derivatives. This is capital F, and this is capital G. Okay, so the x partial of f goes right here. So if you come up here and you treat y like it's a 7 and take a derivative, what pops out right here? Is that okay with that? So again, partial derivative, again, those of you who haven't had Calc 3, you haven't seen this material officially yet. But again, you're just going to treat y like it's a 7 and then take a regular Calc 1 derivative. And then in this spot up here in the top right, I again go to the same place, but now I treat x like it's a 7 and then take a Calc 1 derivative. What pops out now? Just negative x. Because if x is behaving like a 7, these terms die. Right? Okay, so now let's come down here to the bottom left. Now I have to go to this g guy, this y prime guy. I have to treat y like it's a 7. Right? This is gx down here. So I'm going to treat y like it's a 7 and take an x derivative, Calc 1 derivative. What pops out down here? Negative 0.5y, is that right? Just reading out the coefficient of x. And again, from x's perspective, these terms die off. Now from y's perspective, if x is a 7, I don't get so much stuff dying off. What goes to the bottom right? So 0.75, right, goes off the y. Calc 1 derivative of y squared is negative 2y. And then if x is behaving like a 7, it's just a coefficient on the y. So this is the Jacobian of this system. Any questions on that? Okay, so that's the Jacobian of the system overall, but as we've discussed, sometimes you want to zoom in on particular points in the x, y plane, the y-x plane there. So if you care about, say, the equilibrium half-half, you take this matrix you just built and plug in half for x and half for y. And just see what you get. Let's do that. Okay, so if I plug in half for x and half for y, let's see, what's that top left entry become? One minus half, right? That's what I get. I think I get just negative half. Yeah. What's the top right become? Negative a half. There's just an x there. Sorry, just a negative x, and x is a half. What's the bottom left become? Negative 0.25. Y is a half, and then you have half of half, negative half of half. I probably can't do this one in my head, right? So if x is a half and y is a half, what happens to that bottom right? Yeah, it turns out to be negative 0.5. I guess I did know it because I already typed it. So there's the Jacobian at that point. Now, of course, if you change points, you get a different matrix, right? Okay, so again, where's my, this system here, this system that I saw when I zoomed in on the point half-half, that system is this system. I'm going to use a different letter than x because I already have an x. But if back in chapter 7, or if in section 9.1, I asked you, like, hey, what's going on with this linear system? What does that look like? If you trace through the process of section 9.1, you'd be like, oh, that system, I know what's happening. It's a stable node. That's what you would have gotten. It looks like that. So this linear thing here is like a tangent line of the original nonlinear thing. At the point, this is all at x equals a half, y equals a half. So again, this is like a linear thing, right? Kind of like a tangent line. Playing the same role as a tangent line. If somebody comes to you and says, hey, this system right here, how is that behaving around the point 0.5, 0.5? You say it's behaving like that. It looks like this particular stable node. And again, I can't really overstate how nice that is. It's such a nice idea. This idea of a tangent line beefed up, you know. Instead of a tangent line, it's a tangent linear system. But the idea is the same. Okay, questions or comments on that? Push it. So is everybody okay with finding the Jacobian at a point? What are you people looking at? Oh, you know, one time I saved Riley's life from a hornet in this very classroom. So don't worry, Riley. I'll keep all of you safe from the hornet. I murdered that thing, didn't I? Remember that? Okay, so before we move on and just finish up the section, I do want you guys to do this on your own. I want you to, there were some other equilibria, right? Oh, sorry, let me make one more comment. So where we're gonna see these things show up is in ecological models. So let's say that this system we're building here, let's say this models the populations of competing species measured in the hundreds. So like, maybe these are like large beak finches, and these are small beak finches or something. That's what the X and Y represent, okay? If you measure them in thousands, 0.5 would be like, oh, 500 of each or something, right? Is it okay with that? So 500 of each, that's an equilibrium. So it's a coexistence of equilibrium because they both exist there, you know? Well, what if I took 500 of one of the populations and I knocked it down some by maybe I hunt too much or something? So that 500 gets knocked down to 400. Well, if the 0.5 looks like this, what's going to happen if I jiggle that point a little bit? They go back. So this is the kind of thing we'll care about in the next section. Coexistence equilibria, are they stable or not? If they're stable, it's good news. If you like the two species, you know, that means that some could die off and they'll just flow right back to where they were. If it's unstable, that can mean like extinction, which is bad, depending on the species, I guess. Okay, so now I want you guys to take 5 minutes to, what was one of the other points? I've lost Wolfram here. Yeah, so think about x equals 0, y equals 3/4. I want you to follow this exact same process. So the Jacobian in general is already done, right? So plug in x equals 0 and y equals 3/4. That's what we said, right? Build that linear system there and then classify it. So classify it from what we did last time. So tell me if it's a stable node, unstable saddle, whatever. So take, I don't know, 5 minutes to do that. This hasn't changed though, right?
Oh, actually, I was.
All right, let's go over this one so we can. I do want to at least do part of the final exercise. It's the one that starts from scratch. So of course the main issue or the main danger on a problem like this, among other things, but one of the main dangers is just plugging in the wrong x and y values or something, right? So of course there are lots of ways it can go wrong. However, with that Jacobian already built over there, we plug in x equals 0, y equals 3/4, and we just see what pops out. So for example, the top right entry is 0, right? For example. What's the top left top left number? Negative 0.75, is that what people got? 1/4? Yeah. So it sounds like by Democratic vote here, we think this is 1/4. Got overruled, Jacob. I forgot the one minus. Yeah, that's fine. Bottom left, what's that? Oh, a minus 3/8 or something? Yeah. And what's the bottom right? Negative 3/4. So people got. Any disagreements in this matrix I built? Okay, so anyway, we now have a linear system that if we zoom in on the original system, we should see that around 0 3/4. So if you want to know what that looks like, then now we're right back in the previous section from Friday. It just boils down to what the eigenvalues are. So let me just see what they are. We've done this plenty of times, right? So again, you're not expected to memorize this. So on an exam, you'll have this chart that characterizes things by, yeah, so one negative, one positive eigenvalue. So when you have two different real eigenvalues that are of opposite sign, that's the saddle point right here. So you know if you zoom in, you get something unstable, and it's going to look like a saddle. And in particular, you also know about the eigenvector lines if you want to know about those. Okay, so that's what this section says. It says if you want to study something nonlinear, just like in Calc 1, when we're studying nonlinear things all the time, if you zoom in enough, you'll see something linear. Okay, so let's just do one from scratch before we go. So in the homework, you'll see a question like this. They'll just say, hey, here's a nonlinear system. I want you to find the equilibria, and I want you to tell you what kind of thing they are if you zoom in. So if you zoom in, what do you see? This isn't the same problem, is it? Okay, it looks a little different. Okay, I was worried I accidentally did the same one. Anyway, so here's one from scratch. So find the equilibria for each equilibrium, find the Jacobian at that point, and then tell me what kind of thing it is. It'll take maybe 10 minutes to do that, and then we'll reconvene. Pedro or Hema, do you guys have any questions?
No, sir. Thank you.
Okay.
I'm sorry, just sometimes I just can't hear with the connected to the Apple TV. You mind just chatting?
Oh, I said I'm okay.
Okay. Hema, are you okay? Okay. So we'll go over this question in a second and then take off. All right, so we're a little short on time, so I want to at least get a couple of these up on the board for your reference, I think. With me here. Okay, so if you see this in the homework, what you have to do is find all equilibria, as it says, right? Find and classify. So the finding part is Wolfram. So is this what you guys got from these 4 points? Okay, the next, you have to find the general Jacobian and start plugging points into the Jacobian. So is this Jacobian correct? Okay, so now we gotta just march through these things one at a time, plug in and see what we get. So if you plug in -1 for X and 2 for Y, can somebody fill in this matrix for me? Where did you get? 1, 1, -2, and then what?
-4.
You guys agree with that? Okay, so if you didn't get that, I imagine you just made some sort of calculation error or something. That's what you should get for -1, 2. So then you scurry off to Wolfram and ask for the eigenvalues, and what does Wolfram give you? Sorry, -3.5, and what did you say? 0.5. Okay. So something like this, right? So then, at this point, maybe you know what that is, but if not, you scurry off to this table and ask, oh, different real eigenvalues of opposite sign. So now you know it's an unstable saddle. So in the homework, this is what you write. This kind of work, There's a Jacobian, here's a point, here's a linear system that models it close to that point. I know it's an unstable saddle because of this. Everybody okay with that? Yeah. So you have to do it 3 more times. Let's just do it 1 more time. And I mean, we can keep going if you want to, but just to point out that you get something different at a different point. One of these is stable, right? Maybe 0, 3 halves is stable. So what people found. Okay, so what's the linear system there? I'm sorry, did you start at top left again?
-1/2 is 0. -3/2 is
That? What you guys got?
Yeah.
Okay, so then what are the eigenvalues on this one? -3 and -1/2. Is that what people got? Okay, so those are both real, both negative, both different. So this is a stable node or asymptotically stable node, if you like. Anyway, that's what this section does. Oh, I think I forgot to actually mention the theorem. We keep using it, but there's a theorem in the text. The main theorem of the section just says this, that like this linear system here approximates the original nonlinear guide near this point. So that's all it's saying. That's what we've been saying. So again, that's really nice. And there's no real reason to think that'd be true. Like with a tangent line, you can just see it, right? You zoom in, I see a line. What line is it? Well, it's got to go through that point, right? So it's the tangent line there. With this, it's much more subtle. It's not clear why this is true, but I don't know. Again, it's a really nice idea. Very Calc 1-y kind of idea. Okay, so again, this is like what I think all the homework is. There might be one not like this, but that's sort of more conceptual, but this is the bulk of the homework. Any questions on this? You guys feel like you can handle these? All right, so we have spring break, right? Then we can start looking at the ecological models, which is the point of this unit. So again, I won't blame you if you read ahead, but on Friday, we'll talk about competing species models. So see you then.